Hi, good morning to one and all. I am KV Harish, Assistant Professor, Department of Civil Engineering, IIT Kanpur. You are watching MOOC's lecture course on hydration, porosity and strength of cementitious material. Today we will see lecture 14, Portland cement based paste systems, some of the other topics. The textbook and reference materials are shown here. So, the topics covered under this lecture are stages in cement hydration process, understanding setting and hardening process, characteristics of hydration compounds. Overview of the course is as follows. This lecture will provide details about the different stages in the cement hydration process, the importance of setting and hardening process, and the characteristic of hydration compounds are also discussed. Now, stages in cement hydration process. In the last lecture, we have seen the rate of heat evolution curve, where we saw that with respect to time, initially there is a decrease and constant rate, and then later on the rate of heat evolution increases, further on it decreases, and then it reaches a stable state. Now, this rate of heat evolution curve is actually divided into 5 different stages. Stage 1 is called as heat of dissolution. This usually happens during the first 15 minutes from the time water is added to cement, and the second stage is called as the induction period or dormant period. Approximately it is 2 hours to 4 hours, and the third stage is the acceleration period, which is between 4 hours to 8 hours approximately, followed by the deceleration stage 4, and the final one is the steady state. So, we will see each stage in detail. So, the first one is heat of dissolution, and what basically happens is you have the initial hydrolysis, and there is dissolution of calcium, aluminates, alkali, sulphate ions, all of which we have already seen in the previous lecture, the moment water is added to the cement. So, and the mixture is usually wet, and the hydration process is many times defined by a through solution mode. Now, the kinetics of reaction is explained as chemical control, and it is very rapid, and the chemical process is basically dissolution of ions or initial hydrolysis, and basically during this period the compounds are not really formed, and hence there is very minimal or no importance to concrete properties. The reactions are very rapid. In the second stage, which is called as induction or dormant period, the kinetics of reaction is termed as nucleation control, and the reactions here are very slow, and it takes time for the paste system to release ions, and for the actual reactions to happen it takes some time. So, during this time what happens is the calcium hydroxide basically nucleates, and it requires a certain critical level of ions, and this primarily in terms of concrete properties determines the initial set. The third one is the acceleration stage. In this stage the chemical reaction basically starts, and the reactions are also rapid, and the chemical processes is explained as initial formation of hydration products. Multiple things happen during this time. The first one is a precipitation of calcium hydroxide out in solution. The second one is the calcium silicate hydrate gel starts forming on the surface of grains. Third one is more and more calcium ions from cement grains go into solution, and this basically increases the degree of hydration. Degree of hydration is defined as the amount of cement grains that actually participate in the reaction. The relevance that it makes to concrete properties is that this basically defines the initial and final set period. Some more information about the acceleration period is also provided. The start of acceleration defines the initial set of the Portland cement based paste system, and usually the initial set comes between 2 to 4 hours from the time water is added to cement. The initial set is also the time at which the system no longer can be molded in concrete. Now, more information about acceleration period. The end of the acceleration period indicates the final set of cement. Final set typically ranges from 4 to 8 hours from the time water is added to cement, and final set importance is that the cement paste should have gained a substantial strength so that somebody can actually walk on the surface without any casting impressions. Now, the fourth stage is the deceleration period. This stage in terms of kinetics of reaction is explained as chemical and diffusion control, and the reactions are also generally explained as slow. The chemical process is nothing but continued formation of hydration products, and what happens here is that the calcium silicate hydrate gel coats the cement grains. Water cannot reach the inner portion, very important, and finally the hydration is going towards a diffusion controlled mode. With regard to the system's properties, this period determines the rate of early strength gain. Now, in the fifth stage, which is called as the steady state, it is fully diffusion controlled, continuation of the previous stage, and the reactions are explained to be very slow, and the chemical processes, it is slow formation of hydration products, and this typically happens after 48 hours. The importance that this stage makes to concrete property is that this basically determines the later age strength gain. Now, a little different way of understanding setting and hardening process of PCBPS systems are shown. So, in this figure what you find is the time is basically taken in the x axis and the rigidity of the system is taken in the y axis, and the curve basically shows that it is ranging from 0, indicating that it is a fluid which has 0 rigidity, and slowly it reaches some defined strength. So, as soon as water is added to the system becomes fluid, and slowly from fluid it goes to a plastic stage, and from plastic stage it goes to the initial set which defines the limit at which the system starts losing the plasticity, and then it reaches the final set where the plasticity of the system is more or less completely lost. In other words, the system has gained substantial rigidity that it can start taking loads. Now, the first stage, which is the fluid or plastic, this largely depends upon the amount of water that is present in the cement. In such cases, the system initially behaves as fluid and then goes to the plastic stage, whereas water to cement ratio is low or water content is low, then directly after adding the water to the mixture becomes plastic. So, there is no fluid, but it becomes plastic, and from then on it goes to the other stages. Now, in the figure you also have different levels that are shown. One is the limits of handling, the other one is the beginning of mechanical strength. So, the limit of handling is the time until which one can work with concrete. Many times it is also considered as the time at which the mixture is workable, and once it goes to the next level, mechanical strength, it is completely not workable, and the region between the initial set and the final set is called as the transition stage or setting stage. At the bottom you also see what compounds are primarily formed from the time water is added to cement to the time it gains substantial rigidity. So, at the initial stages you will see that ettringite is formed and slowly it crystallizes, and then you have slowly the formation of C3S and the initial set happens, and then you have final set happens, and then finally you have the hardened paste where the hydration is completely diffusion controlled. There are also other important factors which affect setting and hardening process, and one primary factor is the amount of sulfates that is present in the system. Remember that gypsum is the main source of sulfates in Portland cement, and we have already seen in the previous lectures that the amount of gypsum is primarily dependent on the amount of aluminates, and if this proportion is not properly controlled, then we will have different hydration products. So, what is shown in this table is that in the first column you have a gypsum to tricalcium aluminate molar ratio. In the second column you have the different hydration products that could be formed. So, if you see carefully, for a molar ratio of say approximately 3, which is generally considered to be optimal, you get ettringite as a hydration product. Now, if this ratio decreases, which means the sulfates are present in lower amount or gypsum is present in lower amount, in that case you typically land up getting some monosulfoaluminates in addition to ettringite, and this happens typically at a molar ratio of 3 to 1. Now, if the molar ratio is substantially lower, in other words, if the sulfates are very less present in the system, in such a case you typically land up getting only monosulfoaluminates. This happens at a molar ratio of 1. Now, if the sulfates are present still lower than this value, which is explained here as lower than 1, then you typically land up getting monosulfoaluminate solid solution. And typically when sulfates are absent, then this molar ratio is completely 0. Finally, you get the product hydrogarnet. Now, we are also going to see how the presence of these sulfates or the molar ratio is going to affect the setting and hardening process. So, the figure here shows at one level, at one end you have the C3A content and at the other end you have the sulfate content, and the quantity are not clearly mentioned, but generally they have referred as or low high. So, based on that you have 5 different cases. You can have a low case where the content of C3A is generally low in the entire Portland cement clinker, and the sulfates can also be generally low, but even though both are low, it can still have a molar ratio of 3. So, in the other side what you have is what happens to the setting and hardening with hydration age. So, here you have 4 columns. In one column you have what is happening within 10 minutes, in another column you have what is happening between 10 to 45 minutes, in third column you have what is happening between 1 to 2 hours, fourth one 2 to 4 hours. So, for the case 1 where you have low amounts of C3A in the entire system and you have low amounts of sulfates, but the balance of C3A and sulfate are optimal. In such case the mixture will be workable at the first level, and at the second level between 10 to 45 minutes the mixture will still be workable, and at the third level it will be less workable because ettringite starts forming, and typically we get a normal set of 2 to 4 hours, and the first case is what is a typical case that we prefer to have in the Portland cement based paste system. And in the second case we can also have increased amount of C3A, but at the same time we can also have increased amount of sulfates. Okay. So in such cases also the molar ratio could be optimal, which means the molar ratio approximately equal to 3, where we get ettringite as a hydration product. So in case 2, what we find is that the mixture will be workable, say lower than 10 minutes. At the second level it will be slightly less workable, and in the third stage typically 1 to 2 hours you have the normal set. And remember that the normal set primarily happens because of the formation of ettringite. From the view of general Portland cement based paste system, the first case and second case are preferred, primarily because there is a good balance of tricalcium aluminate and sulfates, although in the first case it is low and in the second case it is high. Now coming to the third case, where C3A is substantially higher compared to the sulfates or gypsum, so that is explained as high-low. In such a case the mixture will be workable during the first 10 minutes, whereas the second level between 10 to 45 minutes the setting of the system happens very quickly. And remember that we have already seen when we discussed chemical reactions that we generally do not prefer quick set. So in the case of high-low case, we have a quick set which happens within 45 minutes, and the fourth case where you have high amounts of C3A and low amounts of sulfate or almost 0% of sulfates, then what you find is that within 10 minutes the entire mixture sets, and this is primarily due to the formation of hydrogarnet and monosulfoaluminates and other calcium aluminate hydrates. And remember that we do not prefer case 3, case 4. And coming on to case 5, where the C3A content is substantially low and the sulfate content is substantially higher than what is actually required to balance. In such case the mixture does not set at all. It is explained as false set. So the mixture does not set within 10 minutes, it does not set within 10 to 45 minutes, or it does not set at all completely. So the purpose of this figure is to indicate that for the regular Portland cement based systems, case 1 and case 2 are preferred and other cases generally are rejected, or we do not prefer other cases. Now moving on to the next level to understand setting and hardening, the system basically undergoes 3 types of changes. One is stiffening, the other one is setting, the other one is hardening. Stiffening is defined many times as loss of workability, setting is many times defined as solidification, and hardening is many times defined as gain of strength. And what you see in this figure is basically the water, which is shown as white region, and the cement grains is shown as black region, and A, B, C, D are the different stages. A is immediately after mixing, B is reaction around particles, which is called as early stiffening, C is formation of skeletal structure, explained as first hardening, and finally D is gel infilling or later hardening. You also see that these particles are explained as unhydrated cement particles, which basically exist at the center once the compounds are formed on the surface, and the hydrated compounds are basically collectively called as cement gel, and with further hydration, so A goes to B, B goes to C, and finally it becomes D. And what you see is that you still have some pores in the system, and these pores are called as capillary pores. We will see more about this information at a later stage. And here also another information is parallel figure is shown for general understanding. Now the next topic is characteristics of hydrated compounds, and primarily what we will see is the major hydrated compounds in the system. So we have already seen that the components of hydrated system includes calcium silicate hydrate gel, calcium hydroxide called as Portlandite, ettringite, AFT, monosulfoaluminates AFM, and you have pores, water filled pores, minor compounds, and unhydrated cement. So typically in a scanning electron microscope images, what you typically find is you have different compounds like monosulfoaluminates, ettringite, and other calcium hydroxide, and this one all clubbed together. So three figures are shown for easy understanding, and remember that we have already seen these figures individually in the previous lectures. Now coming on to characteristics of the major compounds. So we are starting with calcium silicate hydrate gel. Calcium silicate hydrate gel does not have a definite stoichiometry. The structure ranges from poorly crystalline or amorphous fibers to reticular network. Calcium silicate hydrate gel is characterized chemically by its C/S ratio. Remember, C stands for calcium oxide, S stands for silicon dioxide. C/S ratio typically ranges from 1.1 to 2, and many times 1.5 is what we generally find, and the C/S ratio primarily depends on very many parameters, including water to cement ratio, degree of hydration, temperature of hydration, and impurities like sulfates and alkalis. More information about the characteristics of the gel. Calcium silicate hydrate gel occupies 50% to 60% of the solid volume of completely hydrated cement paste. Remember that the system is never completely hydrated even after 6 months or 1 year, but if you take a completely hydrated system, we can approximately understand that 50% to 60% will be calcium silicate hydrate gel. And the importance of calcium silicate hydrate gel is that it is the principal strength giving phase for the Portland cement based paste systems, and the strength is primarily due to combination of covalent or ionic bonding and van der Waals bonding within the very complex structure it has. The calcium silicate hydrate gel has a huge surface area of 100 to 700 meter square per gram, and the exact structure of calcium silicate hydrate gel is not actually known, primarily because the water molecules are very much variable, and we actually need specific models, theoretical models or empirical models to understand the structure of calcium silicate hydrate gel. The second one is characteristics of calcium hydroxide. Calcium hydroxide has a definite stoichiometry and it is crystalline in nature, and it generally occupies 20% to 25% of the solid volume of hydrated cement paste. Calcium hydroxide has lower specific surface area than CSH gel, and calcium hydroxide does not constitute much to the strength of the Portland cement based paste systems. But we have other advantages of calcium hydroxide in the sense that it helps in keeping the pore solution alkalinity approximately in the range of 12.4 to 13.5. This is extremely important from a standpoint of corrosion. What is pore solution and other things we will discuss little later. Now the third one is characteristics of AFT, which is nothing but ettringite. their needles interlock and take up more water. It primarily contributes to the stiffening of the mixture and hence influences setting time. AFT has some early strength, however, since the percentage of tricalcium aluminates are very low, this is not a very big factor in the strength development of Portland cement based paste systems. AFT, AFM and other minor compounds together constitute approximately 15 to 20% of the solid volume of hydrated cement paste, and AFT is extremely sensitive to alkaline environments. So, a figure is shown here to understand at what a sulphate ranges and what pH range ettringite is stable. So, here in the x axis you have the pH, in the y axis you have sulphate concentration expressed in log scale. Remember that pH is nothing but minus logarithm to the base 10 of hydrogen ion concentration. You see that the stability of ettringite is a function of both pH and sulphate ion concentration. So, here in this figure you have different compounds. So, you have aluminate hydrates, you have gypsum, you have ettringite, you have hydrogarnet and you also have portlandite. Typically, if you see the area where ettringite is stable, it is somewhere from here to here. So, in terms of x axis you find that ettringite is stable somewhere between 10.8 pH to about 12.8 or 12.9 pH. Likewise, the sulphate concentration ranges from minus 2.3 to about minus 4.3. Now, moving on to the fourth one, which is monosulfoaluminates. The characteristics of monosulfoaluminate is extremely important, and one important aspect is that we usually do not prefer monosulfoaluminates primarily because of sulphate attack, which is a important durability problem in Portland cement based paste systems. So, we will discuss a little bit about sulphate attack. Sulphate attack is a durability problem in Portland cement based paste system arising primarily due to the presence of monosulfoaluminates. When sufficient, if you get back to some of the reactions that we saw in the previous lecture and see for which case we got monosulfoaluminates, you will find that when sufficient gypsum is not available, the ettringite formed from the hydration of C3A and gypsum reacts with excess C3A to form AFM or monosulfoaluminates. When external sulfates enter PCBPS after hardening, they react with AFM to form ettringite. The reformed ettringite or delayed formation of ettringite does not have enough space as the hydrated compounds have already occupied the available space. Hence, this reformation process develops substantial pressure and creates expansive tensile stresses in the system. The weak PCBPS system basically cracks, and such a deterioration is very popularly referred to as sulphate attack. The reaction occurring during the sulphate attack is as follows. The C4A bar H12, which is referred as monosulfoaluminate, that is already present in the Portland cement based paste system, reacts with the external sulfates in the presence of water to form ettringite. So, this reformation of ettringite basically deteriorates the concrete because of expansive stresses created. So, in summary, we have seen stages in cement hydration process, understanding setting and hardening process, and some of the characteristics of major hydrated compounds. With this, we are completing this lecture. Thank you.